Hey everybody, this is section 5.8, and I think this is a nice way to end chapter 5, as we are going to be kind of putting a bunch of stuff together that we have covered throughout this chapter. And questions like number 1, I'm going to do obviously just one example, but if you look in the textbook at the problems, this isn't exactly the method you will use for every one of these questions. You just kind of have to make a game plan for the information that's given in each. I'd call this like a multiple triangle diagram. Okay, so what's going on here is we're being asked to find the value for x and y, and x is just this like small portion here of the base, where y is the other portion. So x and y together make up the base of the larger triangle. So my game plan is that I'm going to find the length of y using the small triangle. Then I'm going to find the entire length of the base, and I'll use subtraction to help me find value for x. And we're back to degrees, so you need to make sure you have your calculator in the proper mode. I have this angle. I know information about the opposite leg, and I want to know information about the base. So using your acronym SOHCAHTOA, that should tell us that we're going to use tangent. The tangent of 48 degrees is equal to the opposite leg over the adjacent leg, which is length y in this case. And I want to solve for y. Remember our shortcut, if you have a bridge, you can cross it. So I can swap those out. Y equals 500 divided by the tangent of 48 degrees. Make sure you have your calculator in the right mode. So I'm just going to type that into my calculator here, and when I do that, I get 450.20. I'm going to have to check on the rounding. Okay, on these questions in the book, they're going to a whole number, so here's what I would recommend. Any work throughout, I'm going to still go ahead and round it to the 10th place, and then I'll just put my final answers rounded to the nearest whole number. Okay, so we know that y is 450 feet, whatever this might represent. Okay, so the next thing I'm going to do is now I'm going to visualize the other triangle. That's the larger triangle. And just for laziness sake, I'm going to call that whole length B for base. I know information about the 20-degree angle. I have information about the opposite leg. I want information about the base. So guess what? We're using tangent again. Tangent of 20 degrees is equal to 500 divided by my entire base. Using that crossing the bridge method, 500 divided by the tangent of 20 degrees. Okay, and what did I come up with? 1,373.73. Again, I'm just going to leave that as 0.7 for just a moment. And I'm going to go in there and subtract my 450.2. And when I do that, I got 923.53. Now is the time I'm going to go ahead and round. So I will say that x is equal to my 924, rounded to the nearest whole number, and my y value was the 450. Our second type of question in this first video is all about bearings, and bearings are a way to navigate. So in order to do these bearing problems, you need to know your directions. I learned never eat soggy waffles to help me remember that. You maybe have learned something different. Donovan, he says news, N-E-W-S, but that doesn't help me. I go around the thing. So never eat soggy waffles. So bearing is a directional thing that is measured from a starting point to an ending point, and you would use this maybe if you were navigating a ship or something like that. So I think it's easiest explained with an example. So let's take a look at number 2. We're being asked to find the bearing from O, meaning origin, to point A. So that's this guy here. When you measure bearing, as I have in the red up at the top, I said that you always want to measure that from the north or south line. You're always going to measure it from the vertical, and you're going to measure it whatever's closest to that point. So see how point A is closest to this line? Okay, so I'm interested in the degree measure that is in this green area where my cursor is. And we would find that this is 90 degrees total. So we would find that by subtracting the 25-degree angle measure that was given from that to give me 65 degrees. Okay, I would not measure here to here. You don't want it to be above 90 when you're working on bearings. Okay, so 65 degrees is what you're going to put in the middle. And the way that you name this properly is you're either going to write north or south first. And we were closest to the south measurement. So I'm going to write south 65 degrees towards the east. So the first part will either say north or south. North or south. And the second part will either say east or west. Okay. All right, let's take a look at number 3. The bearing from the origin to point B. So again, you want to measure the angle that is to the closest north or south line. So that's going to be this small angle here, and that's the one that is actually given. So smack dab in the middle, you're going to write 35 degrees. Again, written first, you need to put whatever it's closest to. Is it closer to south or closer to north? It's south again. Okay, and then east or west. Is it closer to east? Is it closest to west? It would be to the west. So this would be like if your boat is starting at the origin and I need to get to an aircraft carrier or whatever at point B, how would we look at our compass? And we would travel 35 degrees west of south is what that means. And let's do one more of those. Number 4, the bearing from the origin, again, to point C. And I am going to have to use my subtraction there, 90-degree angle total from north to west there. So that means that this has to be 10 degrees. It's closest to the north and closest to the west. So north 10 degrees west. The last thing we're going to cover in this video is about simple harmonic motion. And I'll try to not get too physicsy with you. I'll leave that for Mr. Reinhard. And this first section here, you probably don't need to write anything. You maybe want to put a heading in your notes that says simple harmonic motion. But I grabbed these images out of your textbook. It is on page 627. And let's look at the first picture on the left. So what we have is a ball hanging from a string, or excuse me, from a spring. And without any pulling or squishing that spring, just when it's hanging naturally, wherever that lands, that ball, we're going to call that the starting position. So you can see they're calling that 0. So if you can imagine what would happen here if I grabbed a hold of that ball and pulled it down, it looks like they're going to pull it down 4 inches. What would happen to that thing? Well, it's going to snap back up and it's going to actually go 4 inches above the starting point, and it's going to continue to bounce. Of course, this is imagining that we don't have any friction or air resistance or things like that. And my picture over on the right hand side would be like if we were snapping a photograph along the way, and it looks like they're doing it every second. If you can see the labels on the bottom. So look at what happens to that ball. Look at the pattern that it makes. It makes a wave. It looks like our sine or our cosine wave. So trig functions can be used to model vibratory motion, things like a vibrating guitar a vibrating guitar string, a swinging of a pendulum, some kind of bobbing of an object that is attached to a spring, just like we have here. We can also use trig functions to describe the radio waves, television waves, things like that. So simple harmonic motion. Okay, this is maybe when you want to start writing some of this stuff down. So the object moves on the coordinate axis in simple harmonic motion if we can use a cosine or a sine wave to represent it. So they give us these 2 equations in our textbook, but I don't want you to worry about memorizing that at all, because this is just like our equation for sine and cosine with some transformations. It's just like this that we saw before, okay? So I actually don't even typically think of the letters W or T. I just still think of it as amplitude and the letter B out in front there. So it says that the motion has an amplitude absolute value of A. That's the maximum displacement. So how high above rest does it go? How far below? Look, at the same way we're going to calculate the period as we did with our sine and cosine graph. So that's awesome. This is the same as 2 pi divided by b. Okay. There are some other things that I want to mention. The frequency. So take a look at this. The frequency. This means how long does it take for one wave to be completed. Look at this. This is the reciprocal of the period. So it won't be difficult for us to find. You just have to remember that you're going to invert that period to find the frequency. The maximum displacement is the amplitude. I mentioned that already. And then the time required for one cycle is 2 pi divided by b. That is the same as the period. So let's take a look at a couple examples with simple harmonic motion. We'll start pretty basic here. This question asks us to graph this equation d equals 10 cosine 2 pi t, and t is measured in seconds, d is measured in inches. Okay, so this is a cosine graph. I know that it has a period change. I better switch away from green, huh? Our period with cosine and sine is calculated by 2 pi and dividing that by b, and our b in this case is 2 pi. So what that means is 1 second. That's going to be one period. So I'm going to take that and cut that in half, and I'm going to cut those in half. We also have a vertical stretch. I know that because of the a value in front, it's positive 10. So on my vertical axis, I'm going to label just like that. Okay, I think I'm ready. Cosine starts high. Typically bottoms out at pi, but we're not using pi because we had a period change. So it's going to bottom out halfway through. And here is my beautiful wave. How much time is required for one cycle? And they're asking us for the period. You can also see on your graph, for us to complete one cycle, but get back up here, it's going to happen in 1 second. That's a way for them to ask us for the period. Okay, my last example in this video is actually number 20 out of the textbook. It says write an equation for the distance of the object from its rest position after t seconds pulled down. Okay. So at t equals 0, the object is 0 centimeters from rest. That means it's going to be starting at rest. Then we must start the clock and we pull it down. So I think it might be wise for you to start with a picture. So at that many seconds, at 0 seconds, we're going to start at rest. And then what's going to happen is that thing is going to get pulled down. And eventually it's going to rebound. And it's going to look like this. So I recommend a quick little sketch. Doesn't need to be fancy because that's going to help you determine whether you have a sine or a cosine function. Okay. More information here. They say that the amplitude is 5. So that means the maximum displacement is 5 above 0 and also 5 below 0. They're telling us the a value in the equation when they give us that. Also, because of the shape of this graph, that's a sine wave, but if you notice, the sine wave's going down first. So when they say that's going down, it's going to flip the graph, and we'll have to take care of that with a negative a value when we write our equation. I think probably the hardest part is the period. Kind of have to work backwards, and you might recall from a previous section that we worked on these. We know that the period is 2.5 seconds, but we kind of have to work backwards. How do you find the period? 2 pi divided by b. So we're going to have to work to find that. If you have a bridge, you can cross it. b is equal to 2 pi divided by 2.5. We don't like fractions and decimals. So for this one, I think decimals and fractions, excuse me. I think we could quickly multiply by 2 for both of those. Multiply the top by 2, I get 4 pi. Multiply the bottom, I get 5. So we now know b. We now know the a value. A is actually going to be negative 5 because of the flip. And I think that's all we need to know there. We don't have any phase shifting going on. Try to write these with the proper letters. They wanted us to use d for distance. And this is a sine wave. I do need to put my a value first. So minus 5 sine, and then put your b value. They call it w in this section in the textbook. It's the same as the b value. And then instead of x, they're using t for time. All right, I think that'll get you through the part 1 problems, and we'll do a little bit more in the second video.